that case, it's just a simple shift. So we can simply say that at any point along this function, his second derivative is always greater than 0. So now we just have a new problem, that is when you have a function that have a second derivative, like a one-dimensional function that have a second derivative always greater than 0, then we want to prove it's convex. Therefore, now we use Taylor expansion in this case. The Taylor expansion in the, let's say, degree of 2, it's written as follows, right? So what we know is the third term right here, we know that it's definitely positive because we know this term is positive as always. So in this case, we'll take the x0 as this term, lambda times x1 and 1 minus lambda times x2, which is the point we want to prove that it's convex. As the middle point between the x1 and x2. And first, we'll take x equals x1. Therefore, we'll get this equation right here. We'll just plug everything back in there, and we'll get this equation. And then we'll also get, wait a second, why there's this greater than, because we said that because the third term right here is positive, so it's greater than. So now we just plug x2 into the function, and we'll get the equation. We'll get this equation, and then we do is we'll multiply the first equation by lambda and the second equation by 1 minus lambda. Therefore, we'll get this equation, and then because this term and this term cancels out, and then this term only have fx0. Therefore, we'll get this equation. It's exactly what we need for the convex. Therefore, we proved that for any function, for any one-dimensional function, that if you have if you have second derivative always positive, then you can say that the function itself is convex. So we proved that all of the lines that is defined on this f is convex. Therefore, we can simply get back here, so f itself is convex.